Good morning, everybody, and welcome to my presentation. My name is Dr. Daniel Sabo. I work at the Georgia Tech Research Institute on a variety of projects. Since this year's presentation is a little different, and since I'm voicing over slides, I figured I'd start off with a picture of myself so you can now put a face with a voice. As you can see from my title, today I will be talking to you about immersion chilling conditions that affect peracetic acid half-life rates. So let's get started, shall we? Currently, peracetic acid, also known as PAA, is used as an antimicrobial agent throughout a typical processing plant in an effort to ensure food safety. Over the last few years, however, there have been a growing number of anecdotal reports that have been calling into question PAA's efficacy in this area. These reports indicate that PAA is rapidly decaying in the chiller where there is a large presence of organic carbon. So what do I mean when I say organic carbon loading? I'm talking about the total suspended solids, total dissolved solids, fats, oils, and greases that are released from carcasses into water during their chilling process. The literature has not provided much, if anything, into the extent of these organic components on PAA's decay. However, there are reports that indicate that pH not only plays an important role. The goal of this research effort is to investigate and determine the effects that pH alone, organic loading alone, and the combination of both pH and organic load have on PAA decay. So for all of our laboratory-based tests we conducted, we utilized a simulated chiller media. This media was created in order to standardize the amount of organic carbon load in our tests to match that of industrial chillers. Again, this organic carbon was in the form of TSS, TDS, and FOGs. Additionally, when pH was considered in our tests, we adjusted the pH of our media to those within range that is used in industry today. To make our media, we added WOGs to water in ratios similar to that used in chillers. This provided a usable media that contains an organic load close to industrial chillers. Now I know you're asking me through your monitors why I didn't just use real chiller media from a processor. I wanted to avoid using water that was already treated with PAA. This PAA and stabilizer that accompanies it would be a contaminant which would skew my results. And speaking of PAA, we used two industrial-grade solutions provided by our partners. They ranged in concentrations from 15 to 22% PAA. For measuring the concentrations of PAA in our studies, we used two colorimetric absorption kits, one from Masters Company and one from Chemetrix. The PAA concentrations from both kits provided similar results for each measurement. So before we started our PAA decay studies in chiller media, we needed to understand how stable PAA is in potable water to act as our control. For this study, 150 microliters of 15% stock solution of PAA was added to potable water and its concentration was measured for a period of time, seen here. From this data, a half-life, or the time it takes for half of the PAA concentration to be consumed, was calculated. It was found for this study that the half-life was 5,400 minutes, or 90 hours, or 3 3/4 days for the PAA to become consumed. This gives us a starting point for how stable this chemical can be without anything to break it down in water. Our next study was to understand how pH would affect the PAA stability. For this, we simply used the potable water and adjusted the pH. One thing to note is that when PAA is added to water, the pH of the solution will naturally drop to around 4.2. What we wanted to see is if pH was maintained at 7, 8.5, or 10, what would the effect on PAA stability be? To accomplish this, we added certain amounts of sodium hydroxide and alkaline solution to the water before the PAA was added. This ensured that any loss would be immediately observed. For pH 7, there is very little to no loss. For the observation window of 80 to 100 minutes, there was little PAA loss. In fact, it would take 1900 minutes for half the PAA to become consumed. For pH 8.5, the PAA is less stable. Over the 120-minute observation window, the PAA drops from about 60 parts per million to about 38. This equates to a half-life of about 200 minutes. And finally, for the pH 10, you can see that for the first 40 minutes, there is a rapid drop in pH, which levels off PAA, which levels off for the remainder of the observation window. For pH 10, it only takes about 90 minutes for a loss of half of the PAA starting concentration. For the next study, we wanted to understand the effects of various organic loads on the PAA stability. For this, we took our concentrated chiller media and diluted it with a range of potable water. We used ratios of media to water of 50-50, 60-40, and 80-20. These ranges resulted in a range of TSS, TDS, and COD from low levels to levels typical of industry. To each of these solutions, PAA was added, trying for a target of 100 parts per million. As with the previous study, the PAA was allowed to mix for 1 minute before time zero was measured. This results of the study can be seen here. For the 50-50 mix, you can see that the initial PAA was around 68 parts per million, which is way lower than the 100 parts per million that was expected. Within the first minute, 33% of the PAA was consumed. This huge initial drop drastically slows, and by 120 minutes, 52 parts per million of the PAA remains. For the 60-40 mix, a similar trend is apparent. 32% of the initial PAA is consumed within the first minute. This loss slows down, and after 120 minutes, 42 parts per million remain, meaning that 58% of the PAA is consumed. Finally, for the 80-20 mix, there is a larger initial loss of 45% of the PAA within the first minute. The PAA for this mixture was consumed at a higher rate than the others due to the higher carbon load. After 120 minutes, 75% of the PAA was consumed. One of the big takeaways for this study was just how much of the PAA was consumed within the first minute of contact. When the previous study was completed, we measured the TSS, TDS, and COD of the various media solutions. The graphs here show the effects of these various carbon sources on the half-life of our PAA solution. As you can be seen that as the carbon load increases, the half-life drops, meaning that PAA is consumed faster. And with the carbon loading similar to that in chillers, the half-life of PAA could be as low as or lower than 80 minutes. And building off of that, we observed that some interesting changes in the media within the first minute. The video that is playing shows what I'm talking about. The PAA was added, and within 45 seconds, a noticeable color change is visible. This is due to PAA's interaction with various sources of carbon within our media. The two pictures show another test with similar results of interaction of PAA with the organic load. It supports the idea that PAA is rapidly consumed when it first comes in contact with organic carbon. Next, we looked at the combined effects of both pH and medium organic load on PAA. For this study, we took our chiller media, added sodium hydroxide to raise the pH to our target level, then added the PAA. The PAA mixed for 1 minute before the initial level was measured. For this initial test, pHs of 6.6, 7.4, and 8 were used. The target PAA concentration was 65 parts per million. Results of this study can be seen here. For the media at 6.6 pH, there was an initial loss of 45% of the PAA within the first minute. Within 15 minutes, there was no detectable levels of PAA within the water. Similar results occurred within the pH 7 and 8 media as well. There was an initial loss of 48 and 53% of the PAA respectively. After 15 minutes, all of the PAA was consumed. The average half-life of all of these studies was calculated to be about 2 minutes. The results raised great concerns, especially the pH 8 results, as this is one of the more common pHs used in the chillers and poultry processing today. We repeated the previous study with a second PAA stock of 22% while focusing on an initial pH of about 8.4. The target PAA levels were higher at 85 parts per million. However, a similar trend as the previous results is apparent. The results can be seen here. There is an initial loss of 21 to 24% of PAA within the first minute. For each of the studies, there was little to no PAA within 30 minutes of the addition of the initial PAA. The average half-life of these samples were calculated to be about 6 to 7 minutes. There's still much work that needs to be done in order to understand these effects, but initial results raise some real concerns on current PAA usage as an antimicrobial in poultry chillers today. So to sum up, pHs above 7 have an adverse effect on PAA stability. Additionally, increasing the organic carbon load within the chiller will cause PAA to decay faster. Finally, there is an obvious compounding effect of pH and organic loading on PAA concentration and stability within a chiller. Depending on the initial concentration of PAA and the organic load, that PAA could be gone within 15 minutes. All this together means that PAA may not be at target concentrations as carbon content within chillers increases throughout a processing shift. And with that, I'd like to thank the Agricultural Technology Research Program for the support of this project. I'd also like to thank all of you for your time and attention. Shown here is my contact information. If you have any comments or questions, please feel free to email me or call me. And thank you once again, and have a wonderful day.